Rajput, and today we are going to start new topic, wave optics. Before wave optics, we already completed the chapter ray optics. So what is the difference between wave and the ray? Actually, a ray of light or the light energy travels in the form of wave. Light energy travels in the form of wave, and straight line path of the light energy is called ray. But there are some instances when path of the light energy is obstructed by a very small object, the size of the object is very small, or light energy passes through a very small hole, then it is found that it deviates from its usual straight line path, and we say that here light energy is showing wave nature. Okay. This wave nature can be explained by the Huygens principle. So today we are going to start discuss Huygens principle, but before learning or discussing about the Huygens principle, before it we start learning about wavefront. So what is the meaning of wavefront? Okay. So the definition of wavefront is, a wavefront is the locus of the points which are in same phase, or to be precise, to be exact, we can say a wavefront is the locus of the points which are vibrating or oscillating in the same phase. Okay, so this is the definition of wavefront. For example, the example of wavefront is, suppose there is a pond and water is still calm. If someone drops a stone in that calm and water which is not moving, then it is observed that circular ripples are formed, and center of these circular ripples is the point where a stone has hit the surface of water. Okay. And these ripples starts growing in size, and circular ripples becomes more and more big. Okay. So more and more bigger circular ripples are formed. Each point on the circumference of the circular ripples oscillates with the same amplitude and same phase. If you look at these ripples carefully, you will find that on the circumference of a single ripple, each particle goes at its maximum height at the same time, and all the particles on the ripples, circular ripples, move down at and in the mean position at the same time. Since their positions are same at the same time, it means that all the particles on the circumference of a single ripple are oscillating in the same phase. But regarding phase, I will not discuss it in detail because there are two reasons. The first reason is, in the class 11, in the chapter of mechanical wave, you would have already studied meaning of phase. The second reason is, in the next class when I will start interference of light, that time I will discuss about phase, meaning of phase. Okay. If we have a point source emitting waves in a uniform isotropic medium, isotropic medium means the properties of medium are identical in every direction. So this kind of medium is called isotropic medium. The locus of points which have the same amplitude and are in the same phase are spheres. So actually this thing is defining, this statement is defining, saying that if you consider a point source, this is a point source, and this point source is oscillating, and because of the oscillations in the point source, whether these oscillations are atomic level or molecular level, but light energy is emitted due to the oscillation in the light source. Okay. So this source is oscillating and emitting light in all the possible directions. Suppose speed of light is v, then after time t, the distance travelled by wave will be Vt. So if you consider this point source as a center and draw a sphere of radius Vt, then this is the circumference of the sphere. Now every point on this surface of the sphere is oscillating in the same phase. Why? Because earlier t time before all the particles were at this source, and since all the particles were at the source, so they were in the same phase. Now after time t, I have selected Vt distance from the source, so all the particles which are at the same distance from the source, that is Vt distance from the source, will be oscillating in the same phase. And if you join all these particles which are oscillating in the same phase at a distance Vt, the shape comes out to be a shape of the surface. So this statement basically saying that wavefront of a point source is spherical in shape. So shape of the wavefront is spherical if source of light is point source. Now consider plane wavefront. The plane wavefront means if source of light is very far away, then the size of the spherical wavefront will be very large. Suppose we consider the sun, then the light is coming from the sun, so the spherical wavefront started from the or emitted from the sun. By the time it reaches at the surface of earth and at the position we are studying it, only a small portion of this sphere is received by us. So that small portion of the sphere can be considered as a plane. So plane wavefront means a large distance from the source, a small portion of the sphere can be considered as a plane. Therefore at large distance from the source, shape of the wavefront is like a plane. So this is the definition of plane wavefront. Another important point is, okay, first discuss Huygens principle. So now finally we have come to the some points which are given by the Huygens, and these points together are called Huygens principle. So the first point is, each point of a wavefront acts as a secondary source of waves. This is very important thing. It is saying that the source itself is a source of light, but if you construct a wavefront at some distance from the source, suppose I consider if this is the point source S, and if I construct a wavefront at a distance x from the source, and all the points on this wavefront of radius x are oscillating in the same phase. So these particles, each point of this wavefront can be considered as a source itself, source of light. So each point situated on this source can be considered, its behavior is like that it is also a source of light, and it emits light waves. These light waves are called secondary wavelets. Okay. So each point of a wavefront acts as a secondary source of waves. Second, wavelets emerging from these points, it is not secondary forces, secondary sources. Secondary sources. So wavelets emerging from these points is spread out in all direction with speed of wave. It means that these secondary wavelets are actually behaving like a actual waves. Okay. So wavelets emerging from these points means the points which are on the wavefront, and each point on the wavefront is behaving like a source itself. So wavelets emerging from these points is spread out in all direction with the speed of wave, but there is a difference. These wavelets which are these secondary wavelets do not have same amplitude in all the direction. The amplitude of secondary wavelets is maximum along the direction of propagation of wave, and in the opposite direction amplitude is 0, it is considered as. Envelope of secondary wavelets gives the shape of new wavefront. What does it mean? It means that suppose this is the original source and this is the position of a wavefront at a distance x. Now you want to find the position of new wavefront. So how will you find? Suppose in time interval delta t, distance travelled by the secondary wavelets is v delta t. Suppose this distance is z, then consider each point on the wavefront as center and construct a sphere of radius z. So, if we consider a sphere, construct a sphere of radius z, suppose this is the sphere of radius z, another sphere of radius z. So, I construct so many spheres of radius z, and center of each sphere is on the position of wavefront. So, if I have to take envelope of these spheres, means take common tangent. This is the common tangent I am drawing on the surface of the sphere. Okay. So, this common tangent I have taken by this red color is the new wavefront. This is the new wavefront. Okay. But secondary wavelets, as per the first statement or first principle, is spread in all the possible direction. So, there must be another wavefront like this, because this is the envelope, this is also an envelope we can say. But according to the fourth point I am just going to present here, amplitude of secondary wavelets is not same in all the direction. The amplitude of secondary wavelets is maximum along the direction of propagation of wave in this direction, and in the opposite direction amplitude is 0. So, intensity at this position is 0. So, this wavefront is meaningless. This wavefront is meaningless. Only those wavefronts are relevant which are propagating along the direction of propagation of wave. Okay. The fourth point is, it is also assumed that amplitude of secondary wavelets is not uniform in all directions. It is minimum in the forward direction and 0 in the backward direction. Uniform in all direction, it is let me make correction here, it is maximum, it should be maximum here. Okay. So, uniform in all direction, it is maximum in the forward direction and 0 in the backward direction. So, these 4 points together makes Huygens principle. This we have to remember. Now, this is the geometrical construction of wavefront. I just explained you already in the diagram. If this is the S1, S2, S1, S2 is the original wavefront. Then consider each point on this wavefront as a new source of secondary wavelets, and suppose we take some distance z as radius, and this point on the original wavefront as a center, and we construct several spheres. Then this is the envelope of the all these spheres. This envelope is the position of new wavefront, and this dotted line, this wavefront which is represented by dotted line, is irrelevant because amplitude of secondary wavelets in the opposite direction is 0. Okay. Now, there is one more point which was later added by Fresnel in the Huygens principle. The point is, Fresnel postulated that secondary wavelets mutually interfere. This statement was added later by the Fresnel, that Fresnel postulated that secondary wavelets mutually interfere. Fresnel concept also helped to explain rectilinear propagation of light and why light gets spread when passes through a pinhole. If size of the hole is very small and if light incident on it, then after passing through hole, diameter of the beam of light will increase. So, it spreads when it is passing through a small hole. So, this postulate that these wavelets interfere mutually explains the property of diffraction. This is the spread of light when it is passing through a small hole or pinhole This is because of the diffraction of light, and diffraction can be explained by this property that secondary wavelets mutually interfere. Huygens principle along with Fresnel's principle modification is called Huygens-Fresnel principle. This is important note. The direction of motion of wavefront and wave is same. Direction of motion is same, but wave is normal to the plane of wavefront. What is the meaning of this? Suppose this is the source and waves are travelling in this direction. This is the direction of propagation of waves. Then wavefront will be like this. This is a wavefront, this is another wavefront, this is another wavefront. So, wavefront is also travelling along the direction of propagation of wave, but this wavefront is perpendicular to the plane of waves. So, waves and wavefronts are perpendicular, but direction of propagation is same. This we have to remember. Now, students, this is very important thing which I am going to explain you. I am going to explain you the procedure, the process of refraction with the help of Huygens principle. Okay, so it will take some time. So look here carefully, because in the JEE examination sometimes questions are asked on this concept directly. So here I have taken A1 B1 is a plane wavefront. I am taking here A1 B1 is plane wavefront. So this is the plane wavefront. S1 S2 S1 S2 is the boundary separating two media. This is medium 1, medium 1, and this is medium 2. Okay. Speed of light in this medium is V1 and speed of light in this medium is V2. And students, I think this is known to you, everybody knows that mu equals to C upon V. As far as absolute refractive index is concerned, absolute refractive index means refractive index relative to vacuum. So it is defined as speed of light in the vacuum upon speed of light in the medium. So mu equal to C upon V. So similarly, refractive index here mu1 is C upon V1 and refractive index mu2 will be C upon V2. Okay. Another thing is, this is the plane wavefront A1 B1, and I just told you wavefront and waves are mutually perpendicular. So this is the direction of propagation of wave. This is a wave, and here I consider this is another wave. So these are the wave, and you must remember one fact that if this is the incident ray and this is the normal, then what is the value of this angle? This angle is called angle of incidence. So this angle of incidence is actually equals to I, which is this angle also. The angle made by this wavefront with the boundary is I. If this angle is this total angle is 90 degree, this angle is I, so this is 90 minus I. This is wave, this is wavefront, these two are perpendicular, this is 90 minus I, so this angle is I. Okay. So this is the angle of incidence. Similarly, this I will explain you later. So A1 B1 is the plane wavefront. Now point A1 of the wavefront strike the boundary first, and B1 is strike the boundary of the boundary separating two media after some time. Suppose time taken by this point B1 of the wavefront to strike the boundary is t. Time is t or tau. Tau is the time. So, this distance B1, B3 taken by the covered by the wavefront, this point on the wavefront in the time interval tau is V1 into tau, where V1 is the velocity of light in this medium. So, this distance is V1 into tau, but this point A1 in the same time will travel in the other medium, because initially at t equal to 0 this point was already on the boundary separating two media. So, in the same time interval, distance travelled by this point of the wavefront is A3, A1, A3, A1, A3, which is equal to V2 tau. So, A1, A3 is the distance travelled by this point on the wavefront in the other medium. A1, A3 equals to V2 tau, and B1, B3 equals to V1 into tau. Okay. So, finally, after time tau, this wavefront A1, B1 has completely entered in this second medium, and position of this wavefront is A3, B3. When this point reaches at this position, just crossed the boundary, by that time this point A1 has reached at this position A3. So, this is the new position of wavefront B3, A3. B3, A3 is the refracted wavefront and A1, B1 is the incident wavefront. Okay. If this angle is R, then this is the angle of refraction, remember. Let me explain you how this angle is the angle of refraction, because this is the boundary, then this is the normal. Ray of light is perpendicular to the wavefront, so this is the incident ray, and this is the refracted wavefront. This wavefront is refracted, so refracted ray will not be perpendicular to this wavefront. Refracted ray will be perpendicular to the refracted wavefront. So, refracted wavefront is A3, B3. So, I am considering a line which is perpendicular to refracted wavefront. Okay. This is the wave, refracted wave or refracted ray. So, this is the angle between normal and refracted ray, it is called angle of refraction. Now, this total angle is 90 degree, because wavefront and refracted ray are perpendicular. So, this becomes 90 minus R, but this is the normal to the boundary, this is horizontal, this is vertical line, this angle is 90 minus R, so it becomes R. So, this angle is the angle of refraction. So, now we have to relate angle of incidence and angle of refraction. I and R I have to relate to prove Snell's law. So, to relate these two, what I do, I consider two right angle triangles. One of the triangles is A1, B1 and B3. A1, B1 and B3. This is A1, B1 and B3. Hypotenuse is A1, B3. A1, B3 is the hypotenuse and perpendicular is B1, B3. So, I am taking sin I. Sin I equals to perpendicular B1, B3 upon hypotenuse is A1, B3. This is sin I, and what is sin R? Sin R I am taking in this right angle triangle which has common hypotenuse. This triangle A1, A3, B3. So, in this A1, A3, B3 sin R equals to perpendicular is A1, A3. A1, A3 upon hypotenuse A3, hypotenuse is A1, B3. I think I have taken here something wrong. Sin I equal to perpendicular is B1, B3 and hypotenuse is A1, B3. This point is B3, so A1, B3, not B2. A1 B3. Okay. Now I divide these two equations. Sin I upon sin R, sin I upon sin R equals to B1 B3 upon A1 A3, because A1 B3 and A1 B3 common hypotenuse will cancel out. So B1 B3 upon A1 A3. B1 B3 is the distance travelled in the medium 1, it is equals to B1 V1 into tau, and it is V2 into tau. Tau cancels out, and we get sin I upon sin R equals to V1 upon V2, and this is the Snell's law. So we have proved that by Huygens principle, we have proved the Snell's law. Okay. But I think not all of you understood that how I can say that this is the Snell's law, because you know the Snell's law in a different form. So what I do, I multiply it by c, speed of light in vacuum, c upon V2 into, and I am bringing V1 here, c upon V1. Their space is not available, so I am moving on the next page. Sin I upon sin R equals to, I am taking sin I upon sin R equals to V1 upon V2, or sin I upon sin R equals to C upon V2, and it can be written as C upon V1. Okay. C upon V2 is the refractive index by definition of the medium 2. This is mu 2 upon C by V1 is mu 1. So now we get mu 1 sin I equals to mu 2 sin R, and this is the Snell's law, and we have proved Snell's law using the Huygens principle. This is the highlight of the question. Okay. Now consider TIR. This is very interesting thing. This you will not find in many books. We are going to explain TIR using the Huygens principle. Okay. So look at the diagram first, try to understand. Here A1 B1 is a plane wavefront, and it is incident wavefront. A1 B1 is the incident wavefront. And A2 B2 is refracted wavefront. It is the refracted wavefront. Okay. We know that TIR happens if ray of light is travelling from denser medium to rarer medium. So this medium I am taking as denser. This medium is a denser medium, and it is a rarer one. This is the rarer medium. Okay. So what happens? This point of the wavefront strike the boundary, and A1 B2 boundary separating two media. Okay. This is the angle of incidence, this is the angle of refraction I just told you in the previous discussion. So, A1 B1 is a wavefront. This point of the wavefront strikes at t equal to 0, and this point of the wavefront takes time tau to reach the boundary separating two media. So, how much distance it has travelled by this time? It has travelled the distance B1 B2, which is equals to V1 into tau. In the same time interval, this portion of the wavefront will travel in this medium, which is a rarer medium. Speed of the wave here is V2. So, during the same time interval, it covers a distance A1 A2, which is equal to V2 tau. And remember one thing, this distance A1 A2 is more because V2 is more. This medium is a rarer medium. Rarer medium means V2 greater than V1. Rarer medium is that where speed of light is more, and denser is where speed of light is less. So, since V2 is greater, so this distance is greater. If this distance is more, A1 A2 is more as compared to B1 B2, since V2 greater than V1 implies that V2 tau greater than V1 tau implies that A1 A2 greater than B1 B2 implies that if this side is greater, this is the common hypotenuse of these two right angle triangles. If this side is greater as compared to this, it means that R is greater than I. Angle of refraction is greater than angle of incidence. Okay. I think you are understanding the discussion easily. So, we have proved one thing, if ray of light is travelling from denser medium to rarer medium, angle of refraction is more as compared to angle of incidence. Till now, I have explained this thing to you, R greater than I, because this length is greater, and we are explaining these things with the help of Huygens principle using concept of wavefront. Okay. Now, if we increase I, if we increase I, if I increased, it means that if we increase I, so this distance B1 B2 will increase, B1 B2 will also increase, this distance will also increase, because if wavefront is falling on the boundary like this, if you take wavefront like this, so you have increased the angle of incidence. So, this point is now becomes more distant away from B2. So, it will take more time to reach the boundary of two media. So, it will take more time, it will cover more distance. So, distance B1 B2 increased. If distance B1 B2 increases, if B1 B2 increases, it means that V1 tau increases. It means that tau increases, and if tau increases, so this distance also increases, V2 tau. If t increases, V2 tau increases. So, it means that V2 tau will increase. If this distance increases, it means that A1 A2 increases. And if A1 A2 increases, if this distance increases, it means that R increases. So, R will increase. So, if we increase angle of incidence, finally this R increases. But if R increases, it increases this distance A1 A2. But A1 A2 is a side of this right angle triangle A1 B2 A2, and hypotenuse of this right angle triangle is A1 B2. Therefore, in any case, whatever be the situation, this side A1 B2 should not be greater than the hypotenuse A1 B2. And if we keep on increasing I, and it results in increasing R, and subsequently it increases distance A1 A2, after certain value of, after a certain time, at a particular value of angle of incidence, this A1 A2 becomes equal to A1 B2, that is, this side of the triangle becomes equal to hypotenuse, and this is the condition which we call condition of critical angle. At this angle of incidence, for I equal to theta c, when A1 A2 becomes approximately equal to A1 B2, this is the situation of just before the TIR, when angle of refraction becomes 90 degree. Angle of refraction becomes 90 degree means this side A1 A2, after increasing angle of incidence, a certain state is reached when this A1 A2 keep on increasing becomes equal to A1 B2. This is the limiting condition when one side of the triangle is becoming equal to hypotenuse. This is called, this angle of incidence is called critical angle. If we increase this angle of incidence further, then this side has to be more than hypotenuse, which is not possible. It means that this wave front will not refract in this medium, and this wave front will return in the same medium. This is called TIR. Okay. So, TIR happens when this side A1 A2 needs to be more in length than the hypotenuse A1 B2. Okay. So, in case of critical angle, what happens? I am taking this right angle triangle and sin theta c equals to perpendicular B1 B2, B1 B2 upon hypotenuse A1 B2, and sin r equals to perpendicular, that is A1 A2 upon hypotenuse A1 B2. But when angle of incidence becomes theta c, this A1 A2 becomes approximately A1 B2. This A1 A2 becomes approximately A1 B2. So, at the place of A1 B2, sin theta c equals to B1 B2 upon, at the place of A1 B2, A1 B2 I am substituting this A1 A2. So, what it makes B1 B2 is basically B1 B2 is V1 t, V1 tau upon this A1 A2 is the V2 tau, tau cancels out, then sin theta c equals to V1 upon V2, V1 upon V2, sin theta c is V1 upon V2, sin theta c equals to V1 upon V2, sin theta c equals to, now what I do, I multiply by c and divide by c and bring V1 here. C upon V2 is the mu2 and this is mu1 by definition. Sin theta c equals to mu2 upon mu1, and this is the critical angle theta c. Theta c we can calculate by using sin inverse mu2 upon mu1. Mu2 is the refractive index of this medium and this is the mu1. Okay. Okay. So, we have explained TIR using Huygens principle. Okay. So, this is the way we explain it. Now, this is the reflection. So, now you can do or you can understand by yourself, because after learning refraction and TIR, you will find reflection is very simple to understand using the Huygens principle. Here we are taking this AB is the incident wavefront. So, this is the angle of incidence and this is the reflected wavefront. This point B reaches at point B dash strike the mirror at point B dash. By the time this point reaches here, this point was already at t equal to 0, this point A was already on the mirror. So, it gets reflected, so since medium is same, so distance travelled during the same time interval is same. So, after reflection it reaches here. This distance is suppose Vt, and this distance will also be equal to Vt. So, this length is equal to this length, and rest of the thing you can do by yourself. Okay. I am just saying that this is the incident wave front and this is the reflected wave front, and using some geometry and the concept I told you while explaining refraction and the TIR, you can do it by yourself. Reflection of light from a point source, reflection of light which is coming from point source. So, if this is the point source, then I told you point source, wavefront of point source is spherical in shape. So, this is the wavefront. As it progresses, size of the wavefront increases, and when it strikes the mirror, this is the wavefront, incident wavefront. This point already on the mirror, so it gets reflected earlier. So, after reflection it reaches here, and this point reaches on the mirror later. So, by the time this point strikes the mirror, this point already gets reflected and has travelled this distance. So, this is the reflected wavefront and this is the incident wavefront, incident, and this is reflected wavefront. Okay. As far as numerical problems for IIT-JEE are concerned, these things are more important for us. Converging spherical wavefront. This is the wavefront, and these are the waves. If waves are converging, the size of the wavefront is decreasing. Remember, these waves are perpendicular to wavefront. This is the wavefront, this is the wavefront, this is the position of wavefront after some time, this is the position of wavefront, and here there will be a point of intersection of all these rays. Suppose these are the rays which are going to converge at this point, then point of convergence will become center of curvature of the wavefront. So, this is the wavefront, this is the wavefront, this is the wavefront, and center of curvature is this point for all these wavefronts. Okay. And size of the wavefront is decreasing. Okay. So, this is the size of the wavefront which is decreasing. Now, consider diverging spherical wavefront. If rays are diverging, then this is the situation, this is the wavefront, this is the wavefront, and waves are travelling like this. So, where is the point of intersection? Point of intersection of these waves is here, and this point of intersection is the center of curvature of the wavefront. Okay. So, these things are very useful, and if you guys got it properly, then you can solve this problem. So, try to solve it. The question says, in the figure shown, M represents a mirror. So, M is the mirror, AB is an incident wavefront, AB is the incident wavefront. Which type of mirror is M if the reflected wavefront is PQ? After reflection, if shape of the wavefront is PQ, that is plane wavefront. If reflected wavefront is plane wavefront, then what kind of mirror this M is? Okay. So, let me explain you first case. This is the mirror M, and incident wavefront is this AB. So, shape of this incident wavefront is like this. It is moving in this direction. Okay. So, waves are perpendicular to the wavefront. and suppose this is the point center of curvature of the wavefronts, then waves are like this, diverging waves. This is the mirror and these are the waves. If this is the wavefront, then rays will be falling on the mirror like this, and these rays are diverging. And in the question they have said that PQ is the reflected wavefront. So if this is the incident, wavefront, and after reflection shape of the wavefront is plane, that is after reflection waves becomes parallel. These are the waves and this is wavefront and these are the waves. Okay. So what kind of mirror out of plane mirror, convex mirror or concave mirror can do this? Let us consider a plane mirror first. If we consider a plane mirror and these kind of diverging rays are falling on the plane mirror, then what happens? These rays will after reflection go like this. Okay. So wavefront will be in this shape. It can't be a plane wavefront. So plane mirror is not a possibility. Now consider a convex mirror. If we consider a convex mirror, and on a convex mirror, if diverging waves are falling like this, these are the diverging waves, then after reflection there is no chance of getting these rays parallel. These rays will go like this, and this kind of wavefront will be formed. The only option now we have is concave. If this is the concave mirror and suppose rays are falling like this, diverging rays are falling, and after refraction these rays becomes parallel, it means that it can happen in case of concave mirror if the object is situated at the focus. So this is the focus, these rays are falling as they are coming from the focus, then after reflection reflected rays becomes parallel. So answer of the first part of the question is concave. Okay, so in this case answer is concave. Now in the second case what happens? Incident wavefront is the same but reflected wavefront is this. Okay, so let us discuss this now. This is the mirror and this is the shape of incident wavefront. If this is the incident wavefront, its center of curvature is somewhere here. It means that rays are falling on the mirror like this. These are the incident rays, and this is the mirror, and in the question this kind of wavefront we get after reflection. So if reflection we get this kind of wavefront, so where is the center of curvature? Its center of curvature is somewhere in this position. So after reflection rays are like this. It means that center of curvature is behind the mirror. Okay. So now it is very easy to understand. This mirror is the plane mirror, because in case of plane mirror it happens only if this is the object rays are coming like this, then after reflection these rays will go in this way, and this is the object, then image will be formed at this position, and if this is the image, then this point, the image point, virtual image point will behave like a center of curvature. So, if this is the center of curvature of the wavefront, then this is the shape of wavefront. Okay. So, answer of this part is plane mirror. Now come to the next question. Read the question carefully first, then I will explain you. In the following figure represents a wavefront AB which passes from air to another transparent medium and produces a new wavefront CD. So, incident wavefront is AB and refracted wavefront is CD. Okay. And some angles are given theta 1, theta 2, theta 3 and theta 4. So, I told you while discussing the wavefront that this is the angle of incidence and this is the angle of refraction. Okay. So, sin I, that is sin theta 1, equals to BD. What we have to find? We have to find basically a refractive index. So, sin theta 1 upon sin theta 4 is the refractive index of the medium. Okay. So, answer of this question is C. Now, come to this question. Read the question, what is happening here. The propagation of wavefront from air to glass as shown in figure. So, here we have air and this is the glass. Refractive index of glass is 3/2, and these parallel lines are wavefront. This is the incident wavefront and this is the refracted wavefront. This point strikes the boundary first, and if you consider only this section of wavefront, then point H strikes the boundary first and point E strikes the boundary at point C after some time. Okay. Suppose this point E takes to reach at point C time t. So, if time taken by point E to reach point C is t, then this is the distance EC travelled by ray of light with the speed v1 in time t, v1 t. In the same duration, this is the distance hg travelled by light in this medium where refractive index is something different. So, speed is different. So, v2 into tau. So, this distance is velocity into time v2 tau and it is v1 into tau. Okay. So, what we have to find, in the same time interval Huygens wavelet at point H will expand to pass through point G. They are saying that a Huygens wavelet at point E will expand to pass through a point C at a distance of lambda 1. This distance they have given, this distance is lambda 1. In the same time interval, a Huygens wavelet at point H will expand to pass through point G in glass. So, it reaches here. The distance hg is, so as I told you earlier, this angle is angle of incidence and this is the angle of refraction. Consider this right angle triangle, then sin I equals to, perpendicular means EC, that is lambda 1, upon hypotenuse, hypotenuse is HC, and sin R equals to perpendicular HG upon HC. So, sin I upon sin R equals to lambda 1 upon Hg. Sin I upon sin R by Snell's law is the refractive index mu. So, we get Hg equals to lambda 1 upon mu, and value of mu in the question is 3/2. So, it becomes 2 lambda 1/3. So, this is the answer of the question. Okay. Now, consider this question. So, actually this question I will discuss after discussing something about path difference. Okay. So, leave it because it needs something some extra concept which I have not discussed today. So, class is about to finish. So, here I am going to give you a question as homework, and you will find this question is very good. Solve this question. This is your homework. Okay. So, students, thanks for watching. This is the end of today's class, and I am leaving this class after giving this question you as homework.